My name is Noah Klugman, and I'll be talking about our work Watching the Grid Utility Independent Measurements of Electricity Reliability in Accra, Ghana. Unfortunately, power quality issues are common around the world to the point where they often hold back economic development. However, many utility companies are not able to sufficiently measure the performance of their grids, which makes any performance issues really hard to fix. And this missing data doesn't just impact utilities, but it impacts different stakeholders on the grid actually in different ways. So for a utility, who is trying to provide reliable electricity to customers without knowing when or where the grid is failing, it's much more difficult to do so. But regulators who are trying to ensure that utilities are operating fairly, when they don't have access to good reliability data, most often they have to depend on self-reported metrics of reliability from the utilities that they're regulating, which, while not inherently bad, is a clear conflict of interest. And also ratepayers who are really just trying to get the highest quality electricity that they could have access to for the least amount of money. Um, you know, in areas where reliability varies greatly, without having access to historic data on reliability, they may decide to invest in opening a business or building a house in an area that it turns out has very poor electricity, which is a potentially disastrous economic decision. And this graph sort of blew my mind. So here's the global smart meter penetration by region from 2019, looking at both energy and water meters. And sorry for the confusing colors. Here, the regions in gray are actually the least covered by smart meters, with only 0 to 10% penetration. So, while one might think that smart meters are a clear solution that have existed for many years to take these types of measurements about grid performance, in reality, this isn't really the environment that much of the world experiences. So this brings us to our key claim, which is that we can detect small and large power outages and power quality issues by aggregating measurements from networked sensors installed at outlets and households and businesses at the edge of the grid, enabling a utility independent, high resolution, and low cost system well suited for deployment in under instrumented areas. So before jumping in, let's give a single slide introduction to the grid. So starting with generation, and these are the large power plants from which emanate high voltage lines, which are then stepped down in the high voltage network to medium voltage lines, which are again stepped down to the lowest voltage parts of the network, which is where the service connections enter households and businesses. So we could use this simple model to talk about how we might detect an outage. So let's say a high voltage outage occurs, and you may have missed it, but we added some sensors here to our simple model to the lowest voltage part of the grid. And this is jumping ahead a little bit, but these are the sensors that we call Power Watch, and they plug in at the outlets of each of these structures. So anyways, let's say a high voltage outage occurs. So this would be an outage where you see the line in the high voltage area past generation go dark. And the consequence this has on the network is predictable, right? It percolates down, so every edge node will experience the outage roughly together in time, all going out together. And if you think about our deployed PowerWatch sensors, what will happen is that each one of these will also experience the outage or loss of power at the same time at each one of the outlets they're installed at. And what this will look like, so for the high voltage outage in the system, each one of these sensors will send the report that they lost power, as well as their GPS location and the timestamp, through the cellular network, which we use as our data backhaul in part because of its wide availability around the world. And this will reach our cloud, and we'll get this information, and what we do is that we actually look for a space-time cluster, as these sensors are all experiencing the same outage, so the time bound should be pretty narrow, and they're all on the same network, so the space bound should be narrow as well. And in this case, with our high voltage outage, we would see this cluster and call it a valid outage. And clustering like this gives us confidence that if this was a real outage, that this was a real outage and not just sensors randomly reporting noise or a participant, unplugging a sensor. So this is the basic sensing methodology. And for the rest of the talk, what we'll do is we'll talk through how we validate the PowerWatch sensor both in the lab and in a scaled deployment, and then how we evaluate the quality of the data returned by our scale deployment, without ground truth, because again, by design, PowerWatch is operating in areas where there's no other existing measurements of reliability to directly compare against. And finally, we could present some early learnings about the behavior of the grid in Accra that we've gathered from this deployment. So in the lab, we were able to implement PowerWatch well within the bounds of our application accuracy. We timestamped power loss and restoration within seconds, sample grid voltage and frequency every 2 minutes, and the resolution of all these samples meets accuracy requirements given to us by the folks using our data. We take GPS location, use the 3G cellular network as our backhaul, and the sensor has a battery backup that lets us stay alive during extended power outages. Our cloud is fairly straightforward. When the data comes in, we put it into a Postgres timescale DB database, and we do our space-time clustering using Apache Spark, which we run from Databricks. For our core data processing, we implement stdbscan, which is a space-time density-based clustering algorithm that requires 2 different parameters, both of which we learn. One we learn in the lab, and one we learn from our deployment. The time density parameter is what we learn in the lab, and we do this by simulating outages across large numbers of PowerWatch sensors in a test bed and looking at the largest time variance between these, which we find to be 100 seconds, and which we use as our parameter. And then we learn our space density parameter from our deployment by calculating the maximum distance between each of our deployment sites, as this is the maximum distance that sensors could be in space. Okay, so how well did PowerWatch perform in the field? So stepping back, one of the interesting things about PowerWatch and this design is that we're actually able to take measurements without relying on a utility for either deployment or management. So we were able to select sites based on characteristics we cared about. Here's one site on the left, and the centroid of a site is a transformer, of which, and for each transformer, we place 3 sensors underneath it so that we can see space-time clusters if that transformer failed. And for installation, it was as easy as just training a field staff member to knock on doors, find a participant, and the sensor was installed as soon as it was plugged in at an outlet. So using this methodology, we enrolled 462 participants in 152 sites for over a year. And the sensors largely performed well. Without going too deep into our uptime graph here, one of the things that's interesting to note is we definitely saw some amount of failure, which we were expecting, but a lot of this failure was able to be corrected by just calling participants and asking them to do a little bit of troubleshooting or plug the sensor back in. We could also look at how well the cellular network supported our deployment. And we found in Accra that we were able to, with some local queuing so that we could replay data if the network went down, we found that we were able to achieve a 97% PDD, which is great, and indicates that we collected, the quantity of data we were expecting. So sort of as interesting as the implementation of the deployment are the questions around how do we validate the data that's collected and whether it's representative of energy reliability in Accra. So to answer this, we first have to ask ourselves whether we're actually detecting outages or whether we're just seeing sort of random noise across a distributed population of sensors. So the first easy way to check this is that we could sanity check against outages that appear in the news, as these actually are some sort of ground truth. So here's an example of an outage, which was a high voltage outage like we saw in our early example, which took place March 13th. So looking at how this shows up in our system, here you see a snapshot of the deployment at 6:38 on March 12th. And the green dots are visualizing sensors that are reporting that they have power. And just a couple minutes later, all of these have turned to red dots, showing that the state of each one of these sensors changed, very close together in time. And demonstrating a truly detected with high confidence high voltage outage. But obviously we're not going to be able to validate everything this way, and we have a ton of clusters. Not everything would be in the news, so we have to use other methods to see the validity of all of our clusters. One method that we use to do this is to ask whether the outages that we see occur in dense clusters as we would expect. So here we see a medium voltage outage and its convex hull. And looking at this, we can see that very few powered sensors are actually within the convex hull of this outage cluster. And finding this relationship or searching for this relationship across our whole data, we find that this holds true actually regardless of the size of the outage. So in the table below, you could see that outages that are very large, that over 30 sensors detect, that even then we found a maximum of only 2 sensors that were powered within the convex hull. And really, if this was random noise, we would not expect this relationship. So, assuming now that we have some confidence that we are actually seeing real outages, we could start to question, how good is our coverage? And one way we could evaluate this when ground truth isn't present is we could actually run an experiment, which we've been calling a dropout study, where we randomly choose a subset of sensors to remove, and then we play back the outages that we detected with the full set of sensors across the sensor subset and see whether information is lost. So here our outage occurs, and each sensor from our subset stops charging. And in this example, which is another high voltage outage, no information is lost, as every sensor detected the high voltage outage and a space-time cluster could be formed, even with the smaller subset of sensors. Eventually, though, we'll start to see instances where we play back an outage that was detected with the full set of sensors over the subset, and information will be lost, and this exhibits the edge of our coverage. So here we randomly choose a subset of sensors and play back an outage, and this is a medium voltage outage happening here at the bottom. And now with our subset of sensors, for this outage, which was previously detected, now only a single sensor will go out, where before 2 would have gone out. And in the experimental context, because we don't have enough measurements to get a space-time cluster, we miss this experiment where we would have caught it otherwise, leading to information loss. Now, running this many times, we can start to see that information contributed by each site is actually often redundant, which is great. So the way that we show this is here on the y-axis, we see S80, which is a metric we define that captures the hours of power outages experienced by a customer, in this case over 3 months. And on the x-axis, we see the number of sensors that we simulate removing. If we didn't have sufficient density, we would expect a large variation or large amounts of information loss as we removed more sensors. But instead, what we could see is that these bounds don't really grow large until we're removing nearly a quarter of the sensors, which suggests that we have sufficient deployment density to be capturing the majority of large outages. Okay, with the bit of time we have left, I could share a couple early learnings from what this deployment captured. Here we're looking at SAFE on the y-axis, which is the frequency of outages experienced by a customer. So what this is saying that is for the month of July 2019, the average customer experienced a bit less than 3 outages. And this data was provided to us by the Electricity Company of Ghana, or ECG, which is the national utility that runs the grid we're studying. And ECG does have automated measurements on the high voltage network and on some of the medium voltage network, which allows them to disaggregate these measurements into high voltage, medium voltage, and low voltage contributions colored here. Now, sort of important to note is this little bit of green here, which is the low voltage, which is shown to really contribute nothing at all to the overall outages seen by the utility. And these are, a single transformer going out or something like that. So we could compare this against PowerWatch, and to do so, because PowerWatch doesn't have a perfect method of differentiating between high and medium voltage yet, we group the medium and high ECG outages into a group that we call large outages. And we compare this against PowerWatch outages of greater than 10 sensors, and we see parity largely, which is exciting, which gives us some insight that our sparsely deployed low-cost sensors experience the same set of outages that the utility is sensing from their automated metering system, but at a fraction of the cost. However, the story gets a bit more interesting when we bring back these low-voltage outages. Remember this small sliver here. And when we look at the PowerWatch detected small outages, we see a drastically different story, at times showing a nearly 2x total increase of SAFE, which is a very different estimate. Again, this is our research system, so we can't claim it's a bulletproof result, but it does provide some evidence that there's more to look into here, and the larger number of outages that our system sees does align more with the common perception that reliability continues to need to be improved in Accra. And just very quickly, we also see similar large amounts of samples outside the nominal voltage range. And this has huge effects on appliance health and the overall usability of the grid, and certainly seems worth exploring further. So to wrap up, PowerWatch was designed to solve a problem that in much of the world, grids are not instrumented at the customer level. And we see this in Ghana, where the utility, which is fairly sophisticated, has automated metering at the high voltage and medium voltage. But we show that PowerWatch, by going all the way to the leaf node, actually sees much more and can do so at a fraction of the cost, even when sparsely deployed. Just quickly summarizing some lessons here, PowerWatch didn't scale easily. Actually, the bulk of our publications leading up to the deployment describe metasystems that we developed to support scaled deployments. And generally, there's a lot of remaining work to be done to make systems like PowerWatch more easily implemented and deployed. Similarly, many of the most interesting challenges with this work was how to validate our data stream without ground truth, and the techniques we proposed nod towards some future work there as well. However, we have some continued success. We've recently scaled this deployment to 1,500 sensors, and we're asked to do so by the government of Ghana. And our new deployment is now acting as a primary data source for both the government of Ghana and the US government, as well as other private firms involved with the monitoring and evaluating a large investment aimed at improving the grid in the city. And the data is also being used by a lot of other researchers. And it's been this wonderful experience of taking and packaging our insights so, that we know not only how to take the measurements, but that, they may be useful towards closing the loop towards the positive impact that motivated us originally to do this work. So in conclusion, this was Watching the Grid, utility independent measurements of electricity reliability in Accra, Ghana. Here we show that we, using sparsely deployed sensors at imprecisely selected households and businesses, we could observe more outages and voltage quality problems than the operating utility saw. We did this at a fraction of the cost, which creates a financially viable path towards taking these measurements for even the most resource-constrained environments. Our deployment methodology is utility independent, which makes it uniquely suitable for regulators and researchers, from freeing them from relying on the utilities that they're studying. And finally, the data that we've collected is the largest high-resolution open-source data set on the experience of electricity customers in a lower middle-income country. And we're releasing this at our GitHub. This work was done at Berkeley, Virginia Tech, UMass. Also, we've spun it off into a small group inline, where we're going to be bringing it into 4 different countries in the next couple months, and we're hiring. So if this is interesting to you, please do reach out. Thank you. I'm happy to take questions.